Hello everybody, I'm Carlo Taticchi and I'm going to present this work that I carried out with Stefano Bistarelli on a concurrent language for argumentation. To give an overview, I'll introduce some background notions on argumentation, then I'll discuss how to label an argumentation framework to identify acceptable arguments, and I'll describe the syntax and the operational semantics of our language. And we will also see that the language can also implement some of the classical belief revision operations. An argumentation framework is a directed graph in which nodes are called arguments and the arrows represent attack relations. The goal in this framework is to identify a subset of arguments that share some good properties. For instance, arguments in a conflict-free subset do not attack each other. And you can use different criteria, called semantics, to obtain different subset of arguments. For instance, the admissible semantics, the complete semantics, and so on. An alternative approach to extension-based semantics is provided by labeling functions that mark the arguments according to some kind of rules. And there is a correspondence between extension and labeling-based semantics. Here the rule is that if an argument is only attacked by out arguments, I highlight it in green, it's called an in argument and is accepted. Out arguments, highlighted in red, are arguments that are attacked by at least an in argument, and all the other arguments are undecided, represented in yellow. A fourth label can be introduced by distinguishing undecided labels between arguments from which I either don't know if they are in or out, or I just don't care. For example, E in this figure could be both in and out, so I just don't know which is the correct label, and I label it undecided. But for argument A, I just don't care. I don't want to give it a label, so I leave it with the empty label, and it's highlighted in gray. And we established a mapping between the four-state labeling and the classical semantics. And we will use this mapping for the definition of our language. The four-state labeling is useful here because there is a strong connection between labels and the state of the AGM framework, the framework for which classical operation of belief revision are provided. And we will see that we can indeed implement those operations using our language. The language we defined, we called CA, concurrent argumentation language, allows the communication between agents whose knowledge base is represented by an argumentation framework. Going through the syntax, we have a set of actions on the left. An action can correspond to the success that terminates the execution. We can have insertion or removal of part of the argumentation framework. We have the parallel composition, an existential quantifier, and an action can also be an expression E. On the right side of the slide, we can see the list of the allowed expressions. We have two different tests, a credulous one and a skeptical one. We have a syntactic check. We have the non-determinism, represented with plus. We have a prioritized non-determinism that is a sort of if-then-else construct, and we have a guarded parallelism. We can see the details of the operational semantics. An insertion correspond to the addition of a set of arguments and attacks to the argumentation framework. The removal is the opposite operation. With the check, we verify if a set of arguments and attacks exists in the knowledge base represented by the argumentation framework. The credulous test verifies if there exists an extension of the semantic sigma for which an argument A has a label L. And the skeptical test does the same, except that it considers all the possible extensions of sigma. Going on, the parallel composition of two actions succeeds if both the actions succeed. The guarded parallelism instead executes all the operations for which the guard in the inner expression is satisfied and succeeds if some of the actions succeed, differently from the classical parallelism. The non-determinism chooses just one action if its guard succeeds, while the if-then-else construct prioritizes the execution of the left branch when we have two expressions that can be both executed. Belief revision operations of expansion, contraction, and revision, precisely, can be implemented by the CA language by using the constructs we provided. An expansion corresponds to increasing the number of labels of an argument. A contraction decreases that number, and the revision just changes the label from in to out and vice versa. So undetermined and undecided labels are not affected. And to conclude, we established a mapping between the four-state labeling and the classical semantics. We provided the definition of a concurrent language for argumentation, and I show you the syntax and the operational semantics of the language. And here I only mentioned that this language can implement belief revision operators, and in the paper we provide all the details of the implementation. In a different work, we already introduced the semantics of failure to ensure termination of the actions, and we provided a working implementation of the language. As a future work, we want to consider structured argumentation frameworks instead of just abstract ones, and we also want to introduce a notion of ownership for arguments in order to preserve the information related to whom added a certain argument or attack in the framework. And this will also allow us for using a local store for the agents. This concludes my presentation, and thank you for your attention.